Okay, thank you for being here. I'm Kentaro Kuribayashi from Japan. Today, I'll briefly walking you through our research on the development process of IoT systems. I'll be following this agenda. Let's move on to the introduction. In our research, we will tackle two main challenges in the recent development process of IoT systems. The first one is the requirement for frequent updates of IoT devices to meet user needs. The second one is the complicated technology stack of IoT systems that causes efficiency and maintainability problems. How many of you have faced challenges with these problems? This is a common issue, and our research aims to address it. We believe that WebAssembly can be a savior for these problems. To address those issues, let's examine two key points. The first point is that WASM can potentially be used for the dynamic updating of IoT devices. While various approaches have been examined in prior research, WASM has been overlooked. The second point is, in order to achieve dynamic updates of IoT devices, it's essential to implement them in a manner that fits multi-layered IoT systems. Based on these considerations, we'd like to propose two methods. The first approach involved using WASM for the dynamic updating of IoT devices. The second approach is to enable the use of a single WASM binary originating from a single code base across multi-layered IoT systems. This not applies to individual IoT devices, but also allows us to implement the first method throughout the entire system. Alright, let's dive deeper into the detail of our proposed methods. The first one is dynamic IoT applications using WASM. We propose a method where IoT device is implemented as a combination of an application runtime and the WASM runtime. In other words, this approach is to structure the application functionalities as a combination of the core application and functions that run on the WASM runtime. This allows us to update functionalities without rebooting the IoT device, but just by updating the WASM file. We implemented the approach using Elixir and Nerves. Nerves is a platform for IoT development implemented in the Elixir programming language. Also, we implemented a custom Elixir library called WASMTube to combine the core application with functions on the WASM runtime. WASMTube executes functions running on the WASM runtime based on codes from the core application and returns the result to it. In this way, WASMTube acts as a bridge between the two environments. Now, let's look at the sequence diagram that illustrates how we can update the features implemented by WASM. Using our IoT device structure, we can dynamically update functionalities without a full device reboot. When we deploy a new WASM file, WASMTube detects it and updates the runtime, enabling update to the IoT device capabilities. Next, I'd like to discuss the second method, isomorphic IoT systems using WASM, where isomorphic refers to a consistent architecture across different parts of the system. In this approach, we can implement applications in each layer using the same combination structure as the previously mentioned IoT device configuration. Furthermore, with this approach, we can use the same WASM file built from a singular code base in each layer. This approach can simplify the development of multi-layered IoT systems. To provide a practical example of this approach, we developed an image recognition application using machine learning. To show a concrete and practical example is crucial for our proposals. While previous works advocate the utility of WASM for IoT systems, they don't have practical applications. The machine learning model compiled from the original model to a WASM binary can be executed on the applications. This WASM-based machine learning model can operate consistently across all layers in the same manner. Then, I'd like to discuss the evaluation of our proposed methods. For the first proposal, we evaluated using the experiment environment shown in the top right table. Our first method inevitably adds an overhead for WASM code compared to the traditional single runtime application. We measured the overhead in the test environment and confirmed it was about 200 microseconds. The results are shown in the table at the bottom right. If such an overhead is acceptable, the method is effective. For our second method, we measured the execution time of the image recognition task. The experiment was conducted in multiple layers shown in the table. We confirmed that MobileNet V2 ran in about 600 milliseconds on the IoT device implemented by Raspberry Pi 4. If it's acceptable for the requirement for your system, our method works well to realize multi-layer IoT systems. In conclusion, I'll summarize our contributions and discuss potential future directions. We've shown WASM's potential in solving IoT development challenges. With our concrete implementations, we confirmed its effectiveness through quantitative evaluations. We believe the proposed method offers clear directions for enhancing more intricate IoT systems in the areas like MLOps, task offloading to other layers, and federated learning. Thank you for your attention. That concludes my presentation. Thank you very much.